Let's take a look at aromatic compounds. And when I talk about aromatic compounds, we are looking at compounds that contain benzene or structures like it. We will focus on what aromatic means eventually. But if you look at something that contains benzene, it has quite a few different types of functional groups in it. It's got carbon-carbon double bonds. It's got sp2 carbon hydrogen. And specifically for this one that we're looking at, this is a compound called ethylbenzene. It's got sp3 carbon hydrogen bonds in it as well. So let's try to identify all of these. So if we go again, start at the hydrogen region. So around that 3000 mark, just above 3000, that's the sp2 carbon hydrogen signal. And right below 3000 is the sp3 carbon hydrogen signal. Now the if we should have carbon-carbon double bonds, and we do actually kind of see that here represented by those two signals. We got carbon-carbon double bonds just around 15 to 1600, which is where we'd expect them to be. The reason we see kind of two different carbon-carbon bonds, double bonds, is imagine this side here, or that double bond, looks a little bit different than, say, this one. And so they're going to have slightly different absorptions. It's not your job to know which one's which, but that's why we see two carbon-carbon double bond signals there. Now, another thing that distinguishes this from a typical alkene is these things here. They're called combination bands. Not sure why they call them that, but that's what they're called, combination bands. And these are unique to benzene. You don't see those in alkenes. But if benzene is present, you do see something like that. And you don't have to label each one. You just, if you're kind of going through the process, you like circle it. Oh, those are combination bands. I probably have benzene. So let's look at another example here. So this is the structure that is represented by this IR. And let's again just kind of start at our hydrogen region. Notice here we have something we haven't seen before. Got a couple of signals here around 3500. That is our NH signal. Now, there's a reason why you see two signals there. There are two NH signals if the nitrogen has two hydrogens on it. They call that a primary amine. If the nitrogen had just one hydrogen on it, or what's called a secondary amine, you would just see one NH signal. So that's something you always keep in the back of your mind. Now I go a little bit further to the right. Notice right above 3000 there is the sp2 carbon hydrogen signal. Right below 3000 is the sp3 carbon hydrogen signal. And then I got some carbon-carbon double bonds here between 1500 and 1600. And since I have benzene, these things here, I'm just going to call those my combination bands. And again, those are unique to benzene. You do not see those with alkenes. All right, let's take a look at functional groups that contain an OH or compounds that contain an OH group. So here we have an alcohol. And one of the things that should stand out to you right away, how do you know you have an OH group, is you're going to see a very large broad signal in the hydrogen region. That's going to be indicative of an OH group. And this right here, right below 3000, is going to be the sp3 carbon hydrogen region. Say, do I care about all this other stuff here? Nope, we don't. Because when we look at this, and again, we don't typically get structures from IR. The only reason I know like that this is one pentanol, because the site I got it from said it's one pentanol. But if you don't know what the actual name of the compound is, you can look at this and say, oh, I have an alcohol. I don't have anything else here, nothing in my double bond region, nothing in my triple bond region. So I'm pretty sure I just have a regular old alcohol. Now, on this next page, this one is representing again a compound that has an OH group in it. This kind of wide, broad signal here represents an OH, but this is a unique type of OH. So what I want to do is bring your attention to another signal that we have not seen yet, and that's this one here at 1700. So like 1500 to right below 1700 is carbon-carbon double bonds, something we're there. After 1700 is carbon-oxygen double bonds. Now, if I have a carbon-oxygen double bond and I got this OH signal that's like kind of obliterating everything, so notice how wide and broad it is. Compare the way that looks to the one we just did here. They both represent OH groups, but they look differently. This is how the OH would look for a carboxylic acid. And so I'm basically combining these two pieces of information here to tell me this compound, whatever it is most likely a carboxylic acid. Now, what else do I know about it? Well, it probably does not have any carbon-carbon double bonds. It does not have any carbon-carbon triple bonds. There's nothing there. So I know it's just got carbon-carbon single bonds. If I look at the name of it up here, this is the actual structure. But again, I'm not going to get that just from looking at IR. I get that because I looked at the name of the compound here. On an IR, when you do this on in lab or on an exam, you're not going to have the name in front of you. You're just going to be able to look at the spectra, circle the major things that are there, and just say, well, I think this is a carboxylic acid because I have a carbonyl peak and I got a very wide OH group that kind of obliterates the hydrogen region.